you will very often see inclined plane type questions because they're quite helpful, because you can have students calculate how fast something will slide down the plane. You can have them calculate whether it will slide down the plane depending on the values of the friction coefficient and the masses of the surface, the angle and so on. You can have students calculate what happens with something that's rolling up the plane and how far it will get. So there's lots of kind of interesting physicsy, motiony questions around the use of inclined planes, which is one of the reasons that they appear. And again, this is quite a historical piece, just like projectile motion came out of war, firing cannons, figuring out how far they would go. Inclined planes, obviously, if you want to get something up some stairs, you want to maybe slide it up a ramp rather than carry it upstairs. Like, there's lots of applications in everyday life where we use a plane, even just hills and slopes. If a road engineer wants to figure out what the maximum slope should be for a safe road, they can use this kind of calculation to figure out, well, if we go any steeper than this, we're going to cause dangerous problems where people can't stop properly on the hill. So we'll need a little bit of trig to do this, a little bit of trigonometry. It's not particularly difficult because we're in right angle triangles. We probably talked a little bit about cosine rule and sine rule in relation to vectors a while ago, but this is actually even easier than that because it's right angle triangles. And we're pulling together a whole bunch of the bits and pieces that we've talked about already. So just as we used for projectile motion, we used vectors. We had a horizontal velocity vector. I didn't talk so much about vectors, I just talked about horizontal velocity, but we can represent that with a vector. So horizontal velocity vector and a vertical velocity vector. The vertical velocity vector is kind of interesting because it starts out big because you're going fast upward. And as you go up, it gets smaller and smaller because you're going slower upward. The vector is a line that points upward at this point. It's getting shorter and shorter and shorter, gets to the top, gets to 0, and then the vector becomes a line that points downward and gets longer and longer as you go down because the velocity is coming back as the thing falls in the Earth's gravitational field. Sorry, a little bit of a digression there, but hopefully a little bit of revision of what we're doing with projectile motion. In inclined planes situations, we also want two components at right angles to each other because it just makes life easy. If you've got these components at right angles, we can ignore one and deal with the other, and then deal with the other. Does that make sense? So that actually makes it quite a bit easier to deal with situations. But in this case, we don't want vertical and horizontal. We want perpendicular to the plane, so at right angles to the plane, and parallel to the plane, so in the same direction as the plane. Why? Because the perpendicular one is going to determine the friction. So in other words, the force acting of, say, if this is my plane and I've got an object sitting on the plane, the force that's going to cause the friction to stop it sliding is the force of this object on the plane in this direction, perpendicular to the plane. The force that's going to cause it to slide down the plane is going to be parallel to the plane in this direction, right? So we want those two components of forces, the one perpendicular to the plane and the one parallel to the plane. Okay, let's do it with a diagram because that's gang signs. I don't know. Okay, a diagram maybe makes it a little bit simpler. So we've got the ground, we've got our inclined plane. The plane is inclined at an angle of theta degrees to the ground. We don't really care what theta is. We can go any angle from 0 to 90. We could go upside down, but that wouldn't make a lot of sense as an inclined plane question. And if you have a look at the green triangle, it's not super green, but the green triangle there, let me see, I think I even, no, okay. I have a laser pointer, but it's not much use to you because the camera doesn't catch it. So I will just have to kind of do my best point like a person on Sale of the Century act. So we've got the green triangle basically is that vertical line is the weight force of the object. That's the only real force acting. So you've got an object with a mass in a gravitational field. So its weight force, Fw, is its mass times g, the acceleration due to gravity 9.8. So that's the only real force acting. The Earth is pulling on the object. And remember Newton's laws, the object is also pulling on the Earth, but we don't need to worry about that for the moment. But we can divide that weight force out into these two components, parallel and perpendicular. And the little two-line symbol is parallel because it's two parallel lines, and the little line on an angle symbol is perpendicular because it's perpendicular, right? So those are just little subscripts that we use to avoid writing out the long words parallel and perpendicular. Now, what the key piece here is that angle in that triangle, the green triangle, is also theta by similar triangles. You might have to kind of work through that if it's been a while since you played with similar triangles, but hopefully trust me on this, that angle is also theta. It's the same as the angle as of the plane with the ground. So again, if you use your trigonometry, your SOHCAHTOA, sine is the opposite over hypotenuse, cos is the adjacent over hypotenuse. You don't need tan for the purposes of this. Then you find that the perpendicular force, which is the force into the plane, sorry, it's that way into the plane, again, mirror image action going on, into the plane, is given by mg cos theta, and the force parallel to the plane is mg sine theta. So it's just that weight force times cos of theta or sine of theta. And that will give you those two components. So you can figure out what the forces are at right angles, at right angles, perpendicular to the plane and parallel to the plane. And I'm going to leave it there for the explanation talk and do lots of examples in the example video that give you a sense of some of the things we do with inclined planes.